Hello, my name is Neeranut. I'm a representative of Digital Signal Processing team from Florida International University. Today, I will talk about the double SLERP gravity magnetic vector orientation collections, or we call it GMV-D, in a MARG module.
The MARG module tracks orientation by accumulating angular velocity measured by the gyroscopes. This is known as dead reckoning. Orientation is corrected using accelerometer and magnetometer, but the accelerometer records more than just the gravity if the sensor is not static. The magnetic field is distorted in the proximity of large ferromagnetic objects. Our method will use only a strong collection from accelerometer when the module is static, and a strong collection from a magnetometer when we have verified that the magnetic field is not distorted. Each of the collection will generate a full corrected quaternion, QGA for accelerometer and QGM for the magnetometer. But in each case, we will define a semi-corrected quaternion from the gyroscope QG, using the SLERP, which will yield the QSA and QSM. Here is where we minimize the corrections for which precondition is not met. There will be two layers of interpolation. First, QSA result from interpolating QG toward QGA under control of the alpha, the accelerometer trustworthiness. QSM result from interpolating QG toward QGM under the control of mu, the magnetometer trustworthiness. In the second layer, the QSM interpolate toward the QSA under the control of the alpha to yield the effective output of the collections, Q out. There are four possible cases of the output from the collections. Case 0 is where both alpha and mu is close to 0. The overall result will be similar to QG. In case 1 and 2 is where just one of the collection is trustworthy. The output will be similar to that corrected quaternion. In case 3, if both collections are appropriate, we give preference to the accelerometer collection. The control parameter alpha was obtained directly from the MARG module, which is given by the confidence value. The complete working space is initialized as mu equal to 0. As the system continues to be operated, the mu will be updated to the real value in voxel, where the alpha was found to be high, so that we have a valid accelerometer collection for the reference. After a while, magnetometer collections will be possible in many voxels. Here is the overall process of our proposed algorithm showing in the block diagram. As a result, the graph plot showing that only GMV-D at the bottom remain the same performance in both non-magnetically distorted area, the left portion, and the magnetically distorted area in the right portion. The 3D rendering show the commanded orientation in the leftmost column and the orientation from the four methods in the other columns. Only the GMV-D at the rightmost column result close to the commanded orientations. This video shows the output from the three methods, time unfiddling, GMV-D, and GMVS in real time. First, we do the rotations in the non-magnetically distorted area. Then, we move the sensor to the magnetically distorted area and repeat the same sequence. You will see that the GMV-D remain the same performance in both working space. In conclusion, GMV-D only apply a strong accelerometer and magnetometer collections when they are appropriated, and fills the intermediate collected result using two layers of the SLERP interpolations.